All right, good morning everybody. Welcome to it was going to be the last lecture in this series, but we've now added another one in a couple of months' time on Tickle TK, so the penultimate lecture in our EPICS training series. Today I'm talking about, well, the thing is titled EPICS programming, but it's sort of not quite EPICS. It's for people who aren't really programming so much in EPICS, but want to make use of the features, the cross-platform features and so on that EPICS provides, the build system and our LibCom library. So that's the sort of the outline I'm going to be talking about, why we wanted to program, why should you want to program on top of EPICS, what reasons, when would that make sense. And then I'll talk about a reasonable amount of detail about features of the EPICS build system, all the make files and what the variables are that you have available to you and so on. And for that, I'm assuming a sort of a basic understanding of Unix make, although I'm not really talking about targets, but you need to have a reasonable understanding of what make does and how it works and how to program it to make reasonable use of the EPICS build system, although for the simple stuff, maybe you don't. And then I'll also cover some of the facilities available to programmers in LibCom, the common library, which basically sits on top of the operating system. And so LibCom provides a common interface, a common API that any programmers can use if you want to be cross-platform and run on Windows, Mac, as well as Unix and VxWorks and RTEMS. So why would we want to program on top of EPICS? Well, it's a community standard. I mean, those of us who are in the EPICS community, if you have any collaborators, people who you're working with, you might want to share your software with, then they know and understand how the EPICS applications are laid out and how to configure them and so on. So it makes the learning curve for them getting started with your software much easier. We provide, if you're making use of the facilities, then we provide code portability across a fairly wide range of operating systems, the sort of standard operating systems that people use nowadays. So, and writing C code and to a lesser extent C++ code in a portable manner is not always easy. There are interfaces that, they're not quite the same on Windows. You have to change the call and all those kinds of things. So we take care of that with our common library, so that the EPICS APIs are designed to work the same on all of the target architectures, the target operating systems that we support. And so that support covers your standard Linuxes, Macs, Windows on at least 3 different kinds of builds, the Microsoft compiler, the Cygwin compiler, which is the GNU compiler on Windows, and MinGW, which is the GNU compiler, but using the Windows APIs, whereas Cygwin uses Unix APIs. So you've got those 3. Solaris, and also the real-time operating systems, VxWorks and RTEMS, and we have in the past had support for FreeBSD and others as well, so and it's not hard to get those in as well if you need them. So code portability is one of the advantages. And then build portability as well, because compiling code portably is not always trivial. You can't necessarily write make files that will work everywhere. Microsoft has a version of make which they call nmake, which is rather different than some of the others. It's sort of based on some of the original standards, but things have diverged a lot since. Whereas the EPICS make files, the EPICS build system is designed so that it works the same on all the hosts. You just have to set up your build properly for EPICS. If you can put special things in there for individual operating systems if you need to. But in general, the way the build works is the same on all hosts. And again, we have support for all those standard architectures. So if you're wanting to write portable code that will run on lots of different operating systems, this takes care of a lot of the hassles. I'm not saying it's all of them, but certainly a lot of the issues associated with being able to build and run on multiple operating systems. So we'll start by going through the EPICS build system. The EPICS build rules are one of the most advanced I've ever seen anywhere. So we require GNU Make version 3.81 or later. The latest version of GNU Make is about 4 something or other, and that works fine, so I have used that recently. And as I said, I've never seen a similar set of build rules that do as much without external programs. So things like if you're used to building code off the web using auto tools, so you type /configure and so on. iMake, an old thing for some of the older ones, if you may remember iMake, which is associated with building X11 programs. There's something called Premake, which I've never come across, QMake, which is part of Qt. All those things actually generate make files. So you're not actually writing, they're not completely build system themselves. They're still sitting, there's still another tool that converts what you give it into a make file. And then CMake, which is probably the other common one, that can generate make files, or on Visual Studio it generates project files and so on. But it's basically not make file rules as such. It's not, the build system uses other things on top of make. And we designed this to allow multiple target architectures to be built simultaneously in the same tree. I'm not aware of any other build system which actually allows you to do that, or is designed where you can type make once and it builds for all your architectures. Normally you'll have to say, okay, I want to make it for this architecture. Oh, and by the way, here's the directory that you should do all the building in. And then, okay, I now want to make it for this architecture, and here's a different directory you want to do the build for that architecture. So other build systems don't integrate the functionality that we make use of and we actually need in many cases for EPICS applications. The build rules do expect a specific application layout, and so the main parts of that are that we have a configure directory underneath our application's top area, and the configure directory contains release files. The release files then point to other things that we're making use of, other applications that we're linking libraries from or using include files from. And then there are various config and rules files in there, which usually you can ignore. Apart from one, then there's a config site file that you might want to put entries in for your application. But the release files and the config site file are usually the only ones that you touch. The make files themselves then in the rest of the build must have specific content. In all cases, the make files set a variable called top, which is the relative path to the top of your application, i.e. the directory that contains the configure directory. And then the make files, after setting top, they include usually they include the top config file from the configure directory, and then one of several different rules files. We'll come on to those again in a moment. So basically there are 4 different kinds of make file in the EPICS build system. And 2 of them are almost the same. So the one that most people see to start with is what I think of as a top-level make file, and the idea of this one is it basically exists to run make in one of a number of different subdirectories in a specific order, or with a specific order. The difference between the top level and the next one down in the list, the structural, is that the top level supports a few extra targets. So you can add targets in there for making tar files, say, for your application, but by standard it also comes with targets for doing cleaning and uninstalling the whole application and so on, deleting out the install directories. So structural then is the next kind, and that basically just exists to say, okay, I've got a load of subdirectories underneath me, go and run the build in all of those. I've called the third one constructional, which is the one that actually basically does the building, runs the compilers and so on. And then there is another type which I'm calling the startup, which is basically the one that builds. It basically builds the CD commands files. If you're used to using IOCs, that's the IOC boot IOC directories. And the only differences between these 4 different make files are which particular configure rules file they include, and which variables the rules files then examine and tell them actually what to do. But basically, they all include the top config file. Then you have a whole load of variables that you're setting, and then you include one of the rules files, depending on which kind of make file this is. You may in some cases add some extra rules beyond that, but that's basically the differences between these 4 different kinds of make file. So the top level make file, here's an example of a top-level makefile, or basically the contents of it. So we start by saying top. We define the top variable. In this case, because we are the top-level makefile, top is always dot. And then we have to include this configure config file, which sets up a whole load of variables. The main variable that you would actually need to set in this makefile is the DIRS variable, which basically says it's a list of subdirectories, and that tells make go down into each of these directories and recursively run make in each of them. There are also some variables called depend dirs, and the star there basically is it's the name of one particular directory. So it's a directory name, subdirectory name, and it says don't build this directory until all those others have finished building. So you can set up your dependencies that says I can't build my test directory until I've actually built in the source directory, or I can't build my IOC directory until I've actually built my support code, and so on. So the DIRS variable then lists all the subdirectories you actually want to go into, and all the different depend DIRS variables control what the order is that make will build those subdirectories. In general, it doesn't matter too much. You don't have to set the depend DIRS as long as you're doing serial make. But if you have large collections of systems, and this is especially useful for something like Synapse, where they have large collections of different modules, and it's very important that you build the modules in the right order, they want to run parallel make. If you use make -j and you can give it an optional number there, make will actually run lots of compiles at the same time, and so parallel make speeds things up if you have a fast machine with lots of processors on it. And in those cases, make will not follow the order of the order in which the directories are listed in the DIRS variable. It will actually try and build multiple directories at once. So it really matters. It's important that you actually set those depend DIRS if you're doing parallel builds, because otherwise you'll get simultaneous builds and things aren't going to work if subsequent directories builds depend upon libraries that were built in previous directories. The next kind are structural makefiles, and these are, as I said, almost the same as the top-level makefile. The only difference between this template here and the previous one is here, instead of including the rules top after setting all the variables, we're now including rules DIRS. Exactly the same conditions applies as before. So the examples of these kinds of makefiles are if you have an application, an example app, or some other app directory, that's going to be using one of these structural makefiles. And the IOC boot directory, not the individual IOC subdirectories, but the IOC boot directory itself, is a structural makefile. All it does is it exists to, you can put files in this directory, but none of them get built. It exists just to run the build in the lower level directories, so in the individual IOC boot directories. I'll talk about startup makefiles next because those are similarly simple. So the difference here is that now we're including rules.ioc, and the variables that we're setting are different. And these rules, there's a very specific set of rules that get run and files that you're building inside these IOC boot directories. And so there's only really two variables that it listens to. It looks at the arch, which is the target architecture for the particular IOC you're building, and the targets, which lists any additional files that you actually want it to build. And so targets is going to contain one of these four files: the CD commands file for VxWorks, env paths for most of the other operating systems. If you're building on Windows, then you'll want a DLL path.bat file, which allows you to set up the path so it can find shared libraries, find DLLs. And if you're using Cygwin, then rel paths is basically the same thing as DLL path, but for Cygwin. You can also add, if you need an additional targets in there, then you can add extra rules And as with all these things, if you need to add any extra rules, your rules must go after that, after including the system rules file. So basically at the bottom of the file, below those other standard things. It's probably unusual that you would add additional rules, need to make different kinds of files here, but it's possible. So then the main point of the main difficulty, or the place where people spend most of their time working on these, is the constructional makefiles, which is the files that are used for compiling software. So again, we have to set the top variable, and you'll need to adjust that as to how deep in the tree you are. So it's either going to be 2 levels or 3 or 4 or so on. I haven't listed what the variables are there. We'll come back to those. And here the rules include is just called rules. And as I said, any extra rules and dependencies and so on will appear after including that rules file. The other files, I didn't actually mention this, but all those other makefiles don't have to be named makefile. They could be named GNU makefile or lowercase makefile with a lowercase m, and GNU make will still find them. But in this case, these makefiles have to be just makefile with a capital M, because the makefile actually gets used twice, and it specifically knows what the name is of the file. So, as I said, so you can use other names for those other files, but not in this case. And then the variables they talk about, there are many variables that are actually available to control what gets built. I'm going to cover a number of them here, but Chapter 4 of the Application Developer's Guide gives a fuller list of all the things that are available to you. But I will cover the main ones here. So these then control what gets built and or installed. And we have a series of variable names in these constructional makefiles, which basically list the things that you want make to build for you. This is the set of targets that I actually want to output from this build process. And most makefiles won't use more than a few of these. So it's unusual that you would see all these sorts of numbers. But so we have, if you have header files that you're going to want to install in the top include file, top include directory, then you would need to name those, add those names to the inc variable, and that will then install those header files in the top include directory. If you're building libraries, then you would actually name the library, static or shared object libraries, and you name those in the library variable. Loadable libraries are similar to libraries, but they're ones that are generally explicitly loaded by code. So libraries are things that you just link to. Loadable libraries are things like a module that you might be building a module, say, for Python, and so you generate it as a DLL or a .so, and you tell Python, go away and load this .so file. So that's the difference between a loadable library and a library. Loadable libraries are less common, but there are times when you need them, so we do have to support them. Prods, so a prod is then basically an executable program name. On Windows, it would have a .exe in the name. Actually, no, you wouldn't actually specify the .exe here, but because that wouldn't make sense for the other operating systems. But prod basically is the main part of the name of the executable program that you want to be built and linked. We also have test prods, which are also executable programs, but the only difference between these two is prods get installed into the top bin architecture directory, whereas test prods get built but not installed, so they just get kept in the O. architecture directory, and they're going to be run when you're running tests usually. Objs are sort of more of an older style thing for VxWorks. You can, if you want to create object files, the .o files, you could list those in objs. We don't tend to use those very much in 3.14 nowadays, so that one's probably not as relevant. Scripts for things like Perl scripts or Python scripts and so on, those generally only get installed. You might need to do some variable substitution in them, but usually they're going to be installed. So you list those in there, and they get copied again to the bin directory for the particular architecture. If you're building IOCs or associated with those, then database definition files that want to be installed or possibly created. Installed, basically, yes, DBD files, so you list those in the DBD. If you're creating a record type or a menu, if you have a record type or a menu, you want to basically to install the DBD file that you give it, but you also want it to create you an include file that contains the .h file, which contains all your record type definitions, or for the menu, your menu definitions. So you can use DBD Inc. instead of adding it to both DBD and Inc. This is basically DBD Inc. Targets get added to both DBD and the Inc. directory. So it's basically a combination of the two. Database instance files, so .db files or visual database files, and those go in the DB directory if you want them to be installed in the DB variable. And then you may have other build targets, in which case you're almost certainly going to need to add a specific build rule in most cases. So this is for things that we haven't otherwise covered. If there's anything that we've missed out, then you could add those to targets, and they will also be built. In many cases, the name that you specify in these things doesn't include any prefix or suffix. So your libraries, in general, the name that you put into the library is the thing that's going to go after the lib but before the dot. So if you're building libca.a or libca.so, you just specify library equals ca, and then the build system takes care of, oh, I know I need to add the suffix and the prefix to this name before I actually try and build it. And all those named objects that are listed in these variables then get copied into the appropriate install directory as they get built. So into the include, lib, bin, dbd, db, and so on. And there are some others as well. We support access security configuration files. We support ADL files for installing into those, and so on. There's a few others, but I haven't covered here. And you can even add your own sets of targets if you want to. I won't talk about how you do that, but there are ways of saying I have a new top-level install directory. This is the type of the file. It goes here. Go away and do it, and then the system can actually automatically go ahead and do that for you. So this basically says this is what I want you to build. There are times when you might not want to build all those things on all the architectures which your build system is currently trying to build things for. So there are a series of variables which are derived from the ones that we saw on the previous slide, which basically limit the architectures that it actually tries to do those builds on. So anything with _host after it, prod host, test prod host, library host, and so on, these are all will only be limited to building them on host architectures. So specifically, VxWorks RTEMs are not host architectures. On the Mac, the Apple iOS, the iPhone operating system, iPod operating system, is not a host architecture. So it will not attempt to build things for those particular targets if those are set in the set of target architectures that the build is being told to build. So that's how you prevent going into those. Similarly, if you just want to build things on IOC architectures, then you can use the IOC things. However, I think pretty much all our architectures are IOC architectures nowadays. So strictly speaking, I don't think this will do any limits at all. So these are probably redundant nowadays. It used to be that IOC architectures were VxWorks and host architectures were Solaris or HPUX. And that was how you distinguish them. But nowadays, we can build IOCs on everything. So these IOC variable names are less useful. You can also say this thing only builds on Linux or only on VxWorks and so on. So you can actually name a specific operating system architecture by appending _ and the OS class of the architecture. And the OS class is actually set according to the specific architecture of the target. So it's going to be something like Linux, VxWorks, Win32, Darwin. The class is specific. It's usually the same as the operating system name. And even if you have, so you may have multiple VxWorks targets. If you set prod VxWorks, then it'll build for all those VxWorks targets, but not for your RTEMS targets. So here we have examples. I'm saying here I only want to build the library for my embedded targets. So I'm setting library VxWorks equals mydev and library rtems equals mydev. So that will say on VxWorks and rtems, build the mydev library, but don't try building it on Linux or Solaris or Darwin and so on. So that's how those are the variables that you set in that. There's an example for that. How does it know which source files to actually include in the library or the product or whatever it is that you're building? Again, there are a series of variables that control that. Now, if your particular makefile is only building one target, i.e. one library or one executable or so on, then you can add the names of all the source files that you want to include in this thing into the sources variable. Because sources variables get built so that these .c's will be turned into .o's and will be included in every compiled product, so every library, every executable that this makefile builds. So hopefully you're only building it on one or two, or you explicitly meant for these object files to be included in everything that it's building. So normally it's unusual to use this unless you just have a makefile that's building one particular library. If you're only creating one library, but you maybe have some executables as well, then you can use lib sources. So in this case, I've said I'm building one library, and so these are the source files for my library, and I may have other things. I may be building prods that link into that library and so on. But so this says only include these for libraries. So lib sources then are the set of files that only get built into libraries. If you're only creating an executable or one particular product, one binary executable, then you can use the prod sources variable similarly. So here I'm saying my prod, I'm only building my IOC, and so the source files that go into that are my main and my sequence program. And notice here, I'm not just using .c files. You can use CPP files, ST files, anything that the build system knows how to actually turn into a .o file to link into the executable. You can list in the sources directory, and the build system will automatically deal with that. But usually, and this is the way that I recommend for most things, if you're building a series of different things, then you name them. So here I'm building both a library and a product, so mylib, and I put all the sources that I want to include in my library in a sources directory named after the thing that I'm building. So mylib sources, so it will compile these files plus anything in lib sources, plus anything in sources, and put all those together into mylib. Similarly for prod, I'm setting my tool sources, so I'm saying my tool, I only want the .c file, in this case tool.c, but it will also include anything that it's fine that's in prod sources and anything in sources. So you can see why these are less useful for more complex makefiles. So usually this is what you'll find. So anything with a name with sources after it, it tells you it's going to be associated with building that name, and you have to find out what that is, whether it's a library or a product or a script or whatever. So that's how we control what goes into the library. We can also specify source files that you only want to include on a particular operating system. So we have, as with all those variables before, but now we have sources, lib sources, prod sources with an underscore or an OS class after it. So I can actually say, I'm building my library, and I do support all the operating systems, but on VxWorks, I only want this one. On Linux, I only want that file, and so on. There's something else. In addition to the OS class, you can also use underscore default. And this is a little bit complicated, but basically what you're saying is, if I haven't set the appropriate OS class variable for a particular target, it will build the default source names instead. So things that don't have an OS class, it will build the default ones instead. So here's an example that may help that. So I'm building a single library, mydev, And all architectures I want my dev.c. But on VxWorks, I've got a devvx.c file, so my library on VxWorks will consist of my dev and my devvx, or devvx.c. On Artems, instead of the VxWorks one, I have an Artems-specific C file. So here, lib source is Artems, just wants to include that one. I'm not building this for Windows at all. I don't have a Windows version, so it will still compile my dev if I happen to build this on Windows, but there aren't any specific libraries in there. And for all the other architectures, Linux, Darwin, Solaris, and so on, I'm using the default, and those are POSIX-based things. So in this case, it will build those in anything that isn't otherwise named. So I don't have names for Linux, Darwin, Solaris. So it knows to build that one. But I also had to use this. Now, this nil is a special in the makefile, and it basically looks for, it has to be spelled exactly as shown here, minus is on each end and a lowercase nil in the middle. And that basically says, don't build anything for this architecture, even if it's named in the default. So that's basically saying, this is a non-empty OS class variable, but it's just, there's nothing to actually build in this particular case. So there's features there, and I think there's a little bit more description about that in the Application Developers Guide if you want to look at that. Source file location. So normally our source files are in the same directory as the makefile, but they don't have to be. We can tell make to actually search nearby directories by adding a list of those directories to the source dirs variable. So here we give a relative path from, now notice this relative path is from the O dot directory to the directory that contains the source files. So normally source dirs includes ... because that's the parent directory, which is the one that contains the makefile. But we can add other things, so ... / my other files or those kinds of things. So normally these things would contain a ... at the beginning. I think it might be, you might be able to add absolute paths here, but I wouldn't recommend doing that. So normally these are going to be relative paths, and you're probably not going to be going too far away from where you are. So you can actually move your source files elsewhere. We can also, in addition to using those OS class variables to specify the sources that we want to use, if you have the same, if you have a file that implements a particular functionality and you have a version of that file for all the operating systems you're building in, you can name all those files you can give all those files exactly the same name, the same .c name or whatever, and include them in a source directory under OS on the OS class. And what will happen then is when it tries to build it, it will automatically look for them. So you basically say, you list just the name of the file without the OS class part in it, and the build system automatically looks for those source files in this OS class directory. If you have a common file across, say, all the POSIX architectures, then you can also use OS POSIX and all those POSIX OS things, Linux, Unix, Darwin, and Artems is a POSIX OS, so it will search there. First it will search the OS class, then it will search POSIX, and if it can't find it there as well, then it will also search for it in OS default. So that's the last chance. So this is a sort of more of a generic version of the source code that can build on any operating systems. So quite often this might be something, a placeholder that doesn't do anything, but at least it allows the thing to compile. But in these cases, you have to use the same source file name for all the versions in each of the directories, because it's basically, it's been told just to look for that one source file, and it's just looking in different directories for it.
Andrew, this might be a good, correct me if I'm wrong, but one of the things you can't do in source directories is have a directory name with a period in it, right? Is that the delimiter in the makefile?
You can you have question is, can you have directory names with periods in?
We've had problems with people having names of a module and the release being release
That is probably true for release files. I don't think it's necessarily true here at the source.dirs thing if they're local. But yeah, I would avoid periods in directory names. We do use the period as an internal separator for various targets. So, but I don't think that would prevent you from there. But it's certainly wise to avoid that. So that's probably a good idea to avoid using funny characters in names. And of course, be aware that there are some characters that you can't use in names on Windows. So, and also, I mean, while we're talking about that, be aware that on Windows and on Darwin, file names are case preserving but case insensitive in many cases. So you don't want to have two files that only differ in the case of the file name, because if you try and untar that file on Windows, you'll find that one of them will disappear. Those kinds of things. So you need to be a little bit careful about names. Another question?
Underscore, is that allowed?
Underscore, yes. Underscore is used and so on. So that's usually, and in a lot of cases, I've started using hyphens in names now instead. But yes, underscores are fine. Okay. Source file location. So compiler flags. So there are many ways in which you might actually want to add flags to the compiler command line, because you've got things you might have macros that you want to define from the command line or things like that. So there are many different variables that you can use to set flags for the compiler to use. And again, we have, so the user ones are used for all C or C++ compiles. CPP means C preprocessor, not C++. So if you have flags for the C preprocessor, those will go into the user CPP flags things. You can again say do this, but only for compiles that are running on that are for targets on this particular OS class. So we have OS class versions of those user variables, but all these variables will get used for compiling all .c files from this make file. Oh, and yeah, we also have, so we didn't have the architecture, but in this case, for the C flags ones, we have this arch, so you can actually specify VxWorks PPC 604 or something like that in here. So you can actually go down to the full target architecture. There are times when you actually need that. So as I said, these are for all compiles on all the source files that it's building in this make file. Usually, you're probably going to want to say, I only need this flag for compiling this particular file. So this name.c, it will use this C flags, or similarly, you've got CXX flags and CPP flags and so on. I didn't list them all on this slide because there's just no room. But you have the ability to set flags on all these different ways. So there's lots of ways of adding flags if you need to, and if the build system by default isn't using these. But which ones you actually use, again, depends upon which source files you want, which builds you need the flags to appear on. We also have include file search directories. There's variables, so you don't have to use these to set the directories to search for include files, because there's a user includes OS class, and so on, and also the specific name includes, and there's OS class versions of those, and so on. In these variables, you have to remember that you do actually have to include the -i flag before the directory name for the compiler, because these do get passed directly to the compile line. So you need to have a -i and the path to the include directory that you want the compiler to search for those particular headers. Okay, so far we've managed to run the compiler and added any flags that we need. Now we want to be able to link our application together with libraries, either other application libraries or EPICS libraries or even system libraries. And for that, we use a libs variable. And similarly, there's all sorts of different libs variables depending upon actually what you're building and your target. when you put names into this libs variables, leave off the lib prefix and leave off the .a, .so, .dll thing. Those will get added automatically. So executables, if you're building programs in this make file, then and all your programs use the same set of libraries, or at least they all need at least this set of libraries, then you can use the prod libs variable. So here this says that all products, all executables that I'm making in this make file should be linked to libca and libcom. So this is a very common thing that you see in programs. If you're creating a library, so this is for creating a product. If you're creating a library and you need that library to link against other libraries, system libraries or whatever, then there's a libs variable. But we also have this name libs variable for specific products and libraries. So anything that you've listed in your prod or your library variables, you can use this to say, I need to link with my lib as well as CA and COM. Note that if I had this in my make file, I wouldn't need to mention CA and COM here because it would do that one automatically already. And I think the order in which it includes them is the specific ones before the prod ones. But you might need to double check with the documentation on that one. But it does things in the order that you would expect. If you're linking to system libraries, so these are libraries that must be found somewhere from one of the applications that's mentioned in your release file, at least in EPICS base, even if you're not linking to other things like async. If you want system libraries that are not found through the release file, then we have a syslibs variables and all the variations thereof. So this basically says these are system libraries. They're found usually in user lib, whatever, but the compiler knows how to get to these system libraries in most cases, or the target can configure where to find those. So those are for things like, well, you don't need to do libm anymore, but there are some of the operating system libraries or libxml2 or so on. Those kinds of things you would list in the syslibs area, the syslibs file variable. Library locations, so we've said you want to link to those libraries, but we haven't actually told the build system necessarily where they're found. Now, if your applications are in another EPICS module that's mentioned in your configure release file, then you don't need to do anything. It will find them automatically because it looks through all the lib directories mentioned for applications mentioned in the release file. But if the library is not in one of those modules, then you have to tell it whereabouts to find it. If you don't do this, then you'll get a funny error message that basically implies that it's looking for a build rule to create this library. When it's trying to build in this directory, it says, I don't have a rule to create the library at that particular library. And it thinks, well, why is it trying to build my libxml library in my lib directory? It's not. It's found over there. It's because you haven't mentioned it. You haven't told it what directory to search to find the library. And to do that, you set the value of the name underscore dir variable to the absolute path of the library. So if I had a libusb that was found, I'm linking to libusb, and that library I know is in optlocal lib, then this says you'll find libusb in optlocal lib. So now that will link and will build and link properly. Usually, though, you don't really want to put an absolute path name in your application make file, because then you've got to tell the user, if you're giving this code this code to somebody else, you have to tell them, oh, and you have to edit that make file to set the path to where your USB library is. You probably don't want to do that. So normally you would actually use a variable in here, and you would actually set that variable in the config site file, so that then they only need to edit the release file and the config site file, and then your make file will basically use that variable in setting this dir variable. which tells it how to find the particular library. So don't make your users who you give your code to have to edit your make files to be able to actually build your code. That's not friendly. That's pretty much the main point of the build system. There are other cases where you might need to use conditionals, and you're running a GNU make file, so there's all sorts of features that GNU make provides, which you can make use of. And so one of these are the sort of the common two that you might want to use. So here we're saying I want to test to see whether there's a variable set in my configure release file which determines whether I'm going to build a sequence program or not. So this is something that you actually see in the MakeBase app example application. If you look at that, you'll see it has an if-def snc seek, and if the person doing the building has set snc seek in the release file, then we say, okay, yeah, we want to build the sequencer here. If they haven't, then these are the instructions to follow, and you're obviously not going to build that sequence program. There may be something else that you're doing instead. So this is you're using the conditional features of make to determine what to do based on the release file. Similarly, if you're using a config site file, you may have something like have a variable that you set to yes or no. So in this particular case, this is something that you see in recent versions of, I'm not sure if it's async, but I know Area Detector uses this. You're testing a build IOCs variable to see if it contains the value yes, and if it does, then actually you add the lines here to actually tell it to build the IOCs. But if they said don't build the IOCs, then you may do things here, or you can obviously leave the else part out completely if you don't have anything to do in that case. So we can use yes/no questions or other similar sorts of questions there to control what goes on in the build. So, and basically you can use any of the other features of GNU Make that you need to be able to get through this. That's pretty much covers the build system stuff. Do we have any questions on any other questions on build system issues before I move on to LibCom?
Back on slide 10, you have a list of
Slide 10. Slide 10.
Yeah, there's a bunch of utilities in EPICS space that process files, and I don't remember what all of them are, but they're associated with some of these variables, right? Do certain things like you mentioned the one about like menus database definition. Will generate a cookie file for you. Can you comment on what some of the other utilities are that are available?
In general, I mean, so the utilities that we have in base for doing processing. So, I mean, the main, there are, nowadays I'm trying to move more of them to scripts, but there are still one or two others. But yes, so there's utilities to take a menu.dbd file and to generate an enum, an include file from that defines an enum with all the options for that particular menu. So there's I think it's called dbd to menu.h or something like that.
That would get invoked anytime.
And yes, so that automatically gets invoked. You don't need to name it or anything like that. And in fact, that executable has changed names between 3.14 and 3.15. We've renamed that executable. I think so. But that gets invoked automatically on anything which is listed in the dbd variable, or in the dbd inc variable, sorry, and has a name menu in it. So yes, if you have a dbd file that starts with the name menu, and you put it in dbd inc, it will try and convert that into a menu.h file. Similarly, For the record types, anything that I think starts record and is listed in DBD Inc., it will try and generate a record.h file, which is the thing that generates the C structure that's underlying the record, and there's various other things in that file as well. So those are specific to the particular version of base. There are a few other programs in there. There's something if you're writing scripts. There's something for expanding variables, so you can actually put placeholders, macros, effectively into your source files and say, expand out, replace this name with this value. I haven't gone through. I don't even remember exactly all the details of how you actually do that. But you can basically say, I have these variables. Expand out. Take this thing as a template. Expand it out. And install the resulting file as a script. So you can use the scripts there. I think you have to name that in an expand variable. Most of those features will be described in the Application Developers Guide, the build chapter. The build chapter is a little bit out of date now, but I think most things in there still apply, but there may have been some new features that have been added since, and a few subtle things that have changed, but mostly it's still the same. But I'm not sure that I can. I mean, most of those application programs you generally don't need to know what they are or how to use them, because the build system does that automatically. I mean, similarly, if I go to that. No, I went the wrong way. These startup variables. So these targets, CD commands, env paths, those are actually all targets that get created by one particular file called convert release, because these effectively, the contents of these files come from the configure release file. But behind the scenes, the build system knows how to run that program for these particular targets, but you don't need to tell it explicitly how to do that. The build, that's all built into the build system for these particular targets. You can add, if you wanted to add targets to those files, then we actually need to modify the build system as well to say, here's a new target, which is a target that's built by running convert release. Okay, any more questions on the build system, the stuff that we can do with GNU Make? No? Okay, then let's move on to so libcom then is a general purposes facilities library, and there were two main purposes behind this library. It's designed to provide us with a common operating system API across all our supported operating systems. So basically all the operating systems, the applications code doesn't need to say, oh, I'm on Windows, I need to do this. I'm on VxWorks, I need to do that. I basically try to we try to remove the need for conditionals in your applications code if you use the libcom APIs. And also, we use libcom to provide additional general purpose facilities that are useful. So we have facilities that get used by the IOC, but also by channel access and client programs and so on. And I'll talk about one or two of those as well. Libcom itself, in the latest release 3.14.12.5, has 159 header files, some of which are mostly C, some of which are solely C++, some of which are mixed. I obviously don't have time to cover or necessarily even mention all of them. I'm not really going to talk very much about the C++ APIs here. A lot of those APIs were designed for internal use by the channel access library when that was converted from C to C++, and they're not as well documented, but they're certainly they're good code. So if you're interested in using those, In some cases, they're slightly idiosyncratic code, but they work well. So if you want more information on things that I don't discuss, then these are the main chapters in the Application Developers Guide that talk about some of those facilities. So I will cover IOC error logging, but I don't talk about the task watchdog or the IOC shell. And then there's a couple of chapters that basically go through the different sections. So I'm covering some of the things in these areas. And I'm not talking about the registry here. That's IOC specific. But those are the sort of areas that you'd need to look at in the Application Developers Guide. So the things that I'm going to be covering here are APIs for multi-threading and inter-thread communication. So we've got EPICS thread and mutex and the event semaphores. Communication, we have ring buffers and message queues. Talking about process communication, i.e. outside of this process, so standard I/O and standard library, and also, while we're talking about that, string conversions and EPICS string manipulation functions. OSI sock is associated with dealing with network sockets, so there's and that's actually very useful. That's used outside as well because it hides all the distinctions between Windows, which uses this WinSock interface, and Berkeley sockets, which is what most operating systems use. I'll talk a little bit about error logging and the log client, and the macro library. Actually, the macro library has been moved up earlier, but anyway, so we talk about the macro library. There's some functions in some things in there for helping with data types and data structures, so what the standard EPICS types are, and linked list libraries and hash tables and so on. We have stuff to deal with mathematics, the calc engine, which is used in several applications outside of BASE, and math stuff, and if you need endian tests for your CPU. And then I'll finish off by talking about shared libraries and how to use EPICS export and share lib properly. So multi-threading, the main header file for this is EPICS thread, which is designed to provide a generic threading API, as I said, operating system independent. So it allows you to create threads, and the thread creation takes things like a thread name, thread priority, a stack size, and the function you want it to run, and that can have an argument. If the OS does support thread priorities, then they get mapped to a range so that the numbers that you actually pass into the creation are between 0 and 99, but we also provide standard macros that give you suggested high, medium, and low priority threads for doing sorts of local calculations. Similarly, the stack size the actual stack size is going to be architecture dependent, so we provide a way of saying I want a small stack, a medium-sized stack, or a large stack. Again, and that's also if the operating system supports the ability to set the stack size. Some of them don't. So the sorts of things that the thread library supports are sleep, suspend the thread, resume, what's my name, what's my ID, the sleep quantum, which is basically the sort of the minimum tick with which it can sleep for, and then there's also a show routine that talks a little bit about, that prints out stuff about the threads in the system. One specific thing, we deliberately do not have an API to allow you to kill a thread from outside of it. For a thread to exit, it must actually return. And that was, we started out by having a delete or cancel thread API, but the problem with that is there's no way of being sure that this particular thread doesn't own a mutex, doesn't have some resources, or hasn't allocated memory, that just killing it it's never going to go away, or you're never going to unlock the thread. So now your channel access threads may be locked up just because you killed this thread. So that's why we deliberately do not have that API. And so if you want a thread to exit, you have to be able to somehow send it a signal and tell it exit, and it has to then return. And that was a deliberate decision. There is a C++ wrapper class associated with this thread, So you can do the same sorts of things using more standard C++ type methods. Threads, the EPICS thread header also defines something, thread private variables. And that has operations on creating, destroying, and getting and setting values. So these things are a variable which is different on each thread. So you're storing stuff which is specific to the particular thread that you're currently running in. There's no way of getting at the thread variable for another thread, although the thread could actually pass an address of its variable. Could it? No, it can't, because it still uses the get set operation. So no, it can't. You can't. There's no way of getting at a thread from remotely from a different thread. Getting at these thread private variables. They're only set and fetched locally. We also have in EPICS thread this thing called a thread once API. The idea is to guarantee that you want to run an initialization function just once. And so if you are running multiple threads and they all try and run this initialization function at the same time, because they're all starting up some common thing, allocating semaphores or memory or that kind of thing, then the thread once API will ensure that only one of the first thread that got there wins. So he gets to run the function. All the other threads get delayed until the first guy returns. And when the first guy returns, then all the other threads can then carry on. They don't execute the function at all, but they get delayed until the function has been run. So this thread once. There are similar APIs in many other operating systems, but this is our API for doing that. Once you have threads, you're going to want to be able to do things like mutual exclusion, so prevent them doing things at once, and also signaling between threads. An EPICS mutex is a mutual exclusion semaphore which supports recursive locking. So you can actually call within the same thread. If you already own the mutex, you can lock it a second time. You have to unlock it twice then to free it, to release it. But we have that ability. That's a standard part of EPICS mutex. If the operating system supports priority inheritance and deletion safety and so on, then we will provide, the mutex is designed to use that. And the sort of standard mutex operations that you need, creating and destroying them, lock and unlock, a try lock, which basically says lock if you can, but return me with an error if you can't. And we also have a show routine to print information about the internals. And similarly, there's a C++ wrapper class that actually handles locking in a more C++ fashion. In 3.15, we added another API, EPICS spin, which is based on the mutex API. It's for spin lock semaphores. Spin locks can be taken from interrupt level. So if you're writing mostly VxWorks and RTEMS code that actually gets runs at interrupts, EPICS spins can be taken at interrupt level, whereas a mutex cannot. Mutexes can only be taken at task level. So this allows you to do things like that. Spins are also useful between, if you have a multi-CPU, a symmetric multiprocessing system, then you can use spin locks to, spin locks are faster than mutexes, basically. There are cases when you might want to use those, but in general, the most useful thing is for interrupt communication, for locking something that you want to use at interrupt. Spin locks don't work on uniprocessor architectures. Or what they turn into mutexes, if I remember rightly, on some cases. And then you can't use them from interrupt levels, so you need to know what architecture, what OS you're running on. For communicating between an event between two threads, EPICS event provides you a binary semaphore and the usual sorts of create, destroy, and signal. You can wait forever for the semaphore to be set, or you can do a try wait, say is it set, or you can also do a wait with timeout. So if it takes more than this period, it'll return early with an error. And then similarly, we have a semaphore show, and there's a C++ wrapper class associated with the EPICS event object. Beyond just signaling specific events, you may want to pass messages between your threads, and we have 3 different types for there. The message buffer, EPICS ring bytes, defines a buffer for passing variable length messages between threads. So it supports variable length messages, but when you create it, you actually have to give it a particular fixed size. The higher level code must implement locking if it's needed, but the ring buffer is designed so that if you only have a single thread that's writing into the buffer, you don't actually have to do locking on that write operation. And similarly, if you only have a single thread that's getting values out of the buffer, you don't have to implement a lock on that. In 3.15, we've also added, there's a second creation routine, or an argument to the creation routine, which actually creates a spin lock, which then the buffer uses internally. So you can avoid doing some of the locking. You can just use spin locks if you want from 3.15 onwards. And the usual sorts of buffer operations: create, delete, put message of variable size, get message. And you can also flush, say, delete all the messages that are in the queue, and we'll start from scratch. And so in 3.15, then we have this create locked operation as well for creating one, which automatically allocates a spin lock inside the mutex object, and locks that before it does the write or the read as necessary. We also have status queries, so that you can find out from a particular ring bytes object how big it is, what its capacity was when you created it, whether it's full or empty, how many bytes there are in the messages, and so on, how much free space there is. Another version of that code, but slightly different, is EPICS ring pointer. This supports pushing single pointer messages only. Again, you have a fixed size circular buffer, and you only can push or pop a single pointer value onto the queue. As before, the caller must implement locking, and you can do puts and gets from single threads without locking if necessary. We have the internal spin lock. Basically, otherwise, the only difference here is that instead of a variable length message, we only have a single pointer. And then the all singing, all dancing communication is the EPICS message queue. You specify a fixed size queue, and this supports variable length messages that you can be pushed onto the queue. This was specifically designed for use with multiple reader and writer threads, so it actually has internal locks built into it. There is a C++ wrapper class as before, and the usual sorts of operations: create the message queue or destroy it, send a message, try and send a message. So here we might not be able to queue the message because there isn't enough space left in the buffer. With the previous ones, if you tried to push, it would just return an error. In this case, it will delay. A send will delay until there's space in the buffer. If you don't want it, then you can use try send, which says, is the buffer big enough for my message? If it is, put it in. If it's not, return immediately. And you can also do a send with timeout, so that you can say, I want to send, but not unless it takes less than such and such a time. And similarly, we have those same options on receive. And we can also look at how many messages there are pending, waiting to be received from the queue. And there's a show function as well. So that was communicating between tasks. For communicating outside of the application itself, then we have a wrapper for the C standard I/O called EPICS standard IO.h, and that actually includes standard I/O. So in general, you don't need to include that one. Just include the EPICS standard I/O, and that provides a few things. So EPICS SNPrintf, which basically an implementation, or depending upon the operating system, it may just be a wrapper for the standard C99 calls, but not all operating systems support that properly. They don't all behave the same in terms of if there's not enough space in the output buffer. So this thing is designed to behave similarly on all operating systems. So that's why we provide this wrapper. But on those that meet the standard, this just becomes a synonym for snprintf. There's a whole infrastructure in EPICS standard I/O for redirecting, and this gets used within the IOC shell for redirecting standard in, standard out, and standard error streams. So what it has is a per thread setting for each of the standard streams to allow you to redirect all the standard error output, standard output, or that sort of thing into either another stream, which is probably a file in many cases. So you can actually find in a particular thread, get what my standard in is, or set my standard in, and so on. This, as I said, this is mostly used by IOC shell, but it can be used elsewhere if necessary. And then if you want to make use of this, then your code needs to actually include EPICS standard IO redirect, and that will actually redefine the standard stream identifiers and also the functions printf, putS, and putchar. So if you want your IOC shell commands to be able to work properly with IOC shell redirecting, then you don't have to change what you call on your output. You just include this header file, and that will automatically change, ensure that redirect works in the IOC shell. In 3.15, we actually merged this header into EPICS standard I/O, so you have no choice. If you're using EPICS standard I/O, then you support the redirect functionality. There are a few other miscellaneous file and file name functions in here. I probably don't really recommend using these very much. They're old APIs. Specifically, it's things like EPICS temp name and so on, which gives lots of warnings on modern operating systems because they don't want you to use that. That's an old API which is not secure. So these are the main functionality that you'd want from EPICS standard I/O. We have an EPICS standard lib, which similarly includes the operating system standard lib, and this provides similar sorts of things. EPICS strtod. So strtod in many operating systems doesn't actually behave to the standard. It doesn't necessarily support reading in infinities or nans, which we need. So we added this wrapper, and there's a whole test program in libcom tests which basically checks the operating system to see how close to the features that we expect does the operating system work. And so we can implement the things. We have implemented the things that they don't support in our wrapper. If you're doing scanfs, if you're basically converting doubles or floats from strings, similarly, scanf doesn't necessarily on all operating systems support these nan and infinities. So we provide a couple of functions which basically EPICS scan double does a scanf of %lf, and EPICS scan float does an scanf of %f. So you can convert those and know that you'll have those supported. In 3.15, this library is expanded significantly, and I've added a whole load of EPICS files functions which allow us to convert strings into all the different numeric types, and it will also optionally capture a unit string if you had it on the end of that string, and check the value that it actually gets to see whether you've got value overflow or floating point values and underflow and so on. And then all these functions return a standard status error code. So in 3.15, there's more functionality here, and that even includes 64-bit stuff in 3.15, which isn't available in 3.14. So there's more stuff coming into here. String processing, we have an EPICS string.h. Unlike the others, this doesn't actually include the regular string.h header. It's basically a compilation of various useful string functions and also some replacements of the standard routines or standard routines that might not be provided on all operating systems. So we provide useful functions for converting strings to and from C-style escape. So \n will get converted into a real new line character and vice versa. And also for printing strings that may have unprintable characters in them. There's a function in there for allowing you to do that, so that if the user, usually used for debugging serial messages type things, you want to see exactly what the characters are. We have a function in there that does glob pattern matching. So if you have a pattern with a wildcard, a star, or a question mark in it, you can present it with a string and the pattern and say, does this string match that pattern? So you can go through, if you have a list of objects and the user has given you a wildcard, you can compare each of those objects with the wildcard and it'll say yes, yes, no, no, no. And you basically then decide what you want to do based on that pattern. We also have functionality for creating, for hashing strings. So if you want to take a long string and generate a hash value from it so that you can quickly compare it, then there's a couple of functions, and this is useful for this is used for the general purpose hash thing facility, which we'll come back to later. Then also we have, as I said, we have some standard routines that aren't available everywhere. So case-independent string comparisons, so EPICS versions of stir case comp and stir n case comp, and a stir toc, a reentrant version of stir toc. Stir toc by itself is not reentrant, and that's not much useful for us. So we have a reentrant version called EPICS stir toc. And similarly, if you're wanting to allocate memory to duplicate a string, rather than calling strlen and malloc yourself, you can just call stirdup and it'll return you a pointer to the new string and so on. So those kinds of useful kinds of little functions. One of the main string manipulation libraries that gets used quite a lot is maclib, macro substitution library, which was written for us from scratch, and is actually some pretty hairy code in here, but it's a really useful general purpose macro substitution. So all those dollars parentheses and dollars open brace things, all those substitutions which supports multiple variable scopes, and if you have recursives, so you can have variable names that include variables as part of the name and so on, that's all handled by this maclib. And it also handles environment variables, so the IOC shell commands expand out environment variables as part of the command lane, so this is all handled by maclib. And there's the sorts of operations that you've got, creating context and deleting it. You can get particular macros or set macro values, push and pop your scopes so that you can have macros that only temporarily override values. We can actually present it with a list of strings like the arguments to DB load records, where you have name equals value, comma, name equals value. It'll parse that thing for you and turn that into a memory structure, which you can then install into your particular context, expand a particular string that may have values in it, or expand a string that may have environment variables named in it. And there's actually in 3.15, there's a new one that expands a string that both has local macros and environment variables. So there's lots of functionality there. This code is efficient, very efficient. It's reliable and well tested and so on. Unfortunately, the documentation here hasn't fully made it into the application developers guide. So there is some documentation in there, but this maclib readme file actually contains more information about the individual functions. So that's something that sometime I need to transfer that into the application developers guide. But that's certainly well worth using if you're needing to deal with things that use macros or could use macros. I mentioned that we have this network sockets API. OSI sock is basically the front end to all of that. And this provides then, I call it a unified API. It basically means that there's wrappers around everything that's different on different operating systems when associated with creating and using network sockets. But the idea, again, as normal, is we don't want you to have to write special application code for Windows or Solaris or anything like that. If you use this OSI sock interface, then you can avoid having to write anything special to deal with WinSock 2 or those kinds of things. And this actually is used both by base, the channel access client, and the IOC, both the servers, the IOC server and the channel access portable server. And the log client uses it in the log server and so on. But asyn uses this, and even the version 4 PBAccess network code uses uses this API. So it's extremely widely used and reliable. And in addition to the standard Berkeley sockets type interface, it also provides additional routines for things like querying what the network interfaces are, creating a socket and binding it to an address, listening for connections, the IACTL, destroying sockets again. There's specific routines for configuring for broadcasts, and then a lot of routines associated with converting addresses, socket addresses or IP addresses between ASCII, including doing DNS lookups, and if the DNS fails, then returning you an IP address and so on. There's also something in here, if you have multiple threads that are listening on sockets and you basically need to close down or to cancel one of those threads, you might need to know how to actually unfreeze the thread that if it's blocked sitting reading on a socket. And how you do that, there used to be 3 different versions of that, but then we stopped supporting HPUX, and that was the only use for one of those methods. So, but there are still 2 different methods in which you need to close down a socket to unblock that background thread. So we provide a way of finding out what to do on the current operating system. And then there's also APIs for looking up error message strings and so on, because Windows doesn't use str error for that. So you have to use this API. For dealing with errors, if your application, the IOC certainly uses this. If you have errors, you want to return error status values and look up strings associated with status values, then ermdef and erlog handle these kinds of things. Erlog then allows you to log and flush particular error messages. You can also register listeners, so if you want to talk to a new kind of log server, you can write your own log server and register a listener, and then the IOC will send its log messages to that new kind of error system. And there's also APIs to enable and disable whether log messages appear on your application, your IOC console. The IOC log server itself is a separate application that you can use with IOCs or other applications if you want to record what your error messages, what your log messages are, and it stores those messages in a circular buffer file, which may have a max size, or you can just say unlimited. And then you can also do file rotations if you want to change the file every week and just keep the old ones. But you can the log file rotation only works if you change the directory name. You can't actually change the file name part. It only changes the directory name, which is a little weird, but anyhow, that's how it happened. So lots of information about logging in Chapter 10 of the Application Developer's Guide. So I encourage you to go there to find out the specifics. EPICS types, we have standard type definitions for the various different sizes, and just a reminder, a lot of this code predates C99, so whereas nowadays we would say just use C99 standard int 16 types, well, we wrote this before they actually came out, or before it was available on all our architectures, so we provide our own instead. So the usual various different sizes of integers and floats, there's floats and doubles, and an enum. In 3.15, we've added 64-bit types to that, so you can use those. We don't have, the 3.15 doesn't support database fields to be those types yet. Those will probably be coming in 3.16. But EPICS types provides those definitions in 3.15. Unfortunately, one thing to note, EPICS int 8 is always defined as a char. So on some architectures, it's going to be unsigned. You might think this is a signed integer. It isn't always. So it's unfortunately, whoever it was who created that didn't think too carefully about what a char means. It should have been signed char, but it's not. And then EPICS types also defines things like max string size, so the 40-character string limit. You can use that from there. There's a couple of Boolean values. There's an EPICS Boolean in here as well that I didn't talk about, and a macro called string of, which basically stringifies a token if you need to print things, names taken from code. Okay, so I talked about some of the data structure things. Then we provide standard API to link lists. This is heavily used inside the IOC for doubly linked list management. These linked lists are intrusive, i.e. anything that you want to put on one of these linked lists, you have to have an L node data member in your object. But that does mean that the list itself doesn't need any extra memory because it just uses the contents of that L node for the previous and next pointers. And you have your usual operations that you want to do on lists: initialization, find the first and last objects on the list, get the next one or the previous one, insert an object, concatenate two lists together, delete a single object, remove a list of objects from a list, and so on. Insert objects, get the nth object or the step n objects beyond this one, and so on. Standard sorts of stuff. You can statically initialize the nodes and or the lists. This code is very efficient, reliable, and as I said, used in the IOC, so it's certainly well tested. The API was modeled on the VxWorks list lib, but it was rewritten completely, so it is all our code. And some of those things are actually macros, so as I said, that's why it's efficient. We have a general purpose hash table object, so if you need to do fast lookups of things, of object pointers by a name, you can use a GP hash. That uses a standard hash bucket, so you initialize it, you specify how many buckets you want, which has to be a power of 2 between 256 and 64K. You can store multiple kinds of objects in a single hash table. And so as part of the lookup, you specify a type ID, which is really a pointer, which it internally uses to distinguish the objects, and it includes that ID in the hash calculation as well. So you give it a name and this type ID. You can then give it the same name but with a different type ID, and you'll get a different object. It won't clash. This, unlike the list stuff, this is non-obtrusive, so the table actually allocates node objects, so the object that you pass in doesn't have to include anything special to be put in one of these. It provides thread-safe access. There is a mutex built into the hash table object, and you've got all your usual sorts of operations: adding named objects, find by name, delete again by name. You can free out the whole table, or there's a dump for checking to see what you've got in there. The calc engine is a fairly useful general purpose expression compiler and evaluation engine. So there's really two parts to it. One part gets used at compile time, where you basically present a math expression to this function, and it generates, it parses that, returns you with any errors. But if it parses it successfully, then it actually returns a bytecode of the compiled version of that. So the bytecode then allows you to execute that math operation later on with a given set of input values, which all have to be doubles, by the way, very quickly. So again, this is efficient. This code is used within the IOC by the calc and calc out records, and in the transform record is part of Synapse. And error detector plugins are now using this. MEDM uses the calc engine. The alarm handler, I think, even uses the calc engine for some things. And access security uses the calc expressions, so on. So this is widely used and useful for if you just need to embed a simple expression. So the operations that you need are to be able to compile the expression, perform a calculation, but we also have a routine which allows you to examine the bytecode and tell you which input variables are read and which variables are set, because you can have multiple expressions in this string, and the expressions can also include assigning values to variables. So this argument usage function can query the bytecode and say, yes, this reads A, B, and C and sets H and K, so, as well as returning a value. And then there's also a function for dumping bytecode for debugging purposes. As I said, efficient, reliable, and certainly well tested. If you want detailed documentation, the application developer's guide covers all the expressions are supported and so on, how to use this. A few other headers. EPICS math. It includes math.h, but then it also defines a couple of, if you need an infinite value or a NaN value for some purposes, you can actually get to this provides them. And this is also designed to ensure that on all operating systems we have these three macros available: finite, isNaN, and isinf. So if you need to use those, then you can just include this and you know that they're there. As an EPICS endian.h, which is useful for finding out what the byte order is of your CPU. So it defines 4 macros. These two are both numeric macros, and then these two will be equal to one or other of those two, depending upon the particular CPU architecture that you're running on. So you've got things like that. I'm not covering devlib here, but there's a whole separate set of libraries for use talking to actual hardware, which is operating system independent way. It only really, oh no, it does actually, it's supported on VxWorks, RTEMS, and Linux, and you could add support for other operating systems if you had the ability to talk to VME cards or PCI cards from user code on those operating systems. So there is some Linux support if you have certain plugins, certain cards for remotely connecting to VME systems. So devlib I'm not covering in here, but there's that whole library associated with that. I think we've touched on that in earlier lectures, so that's why I didn't include that here. Then the library exports, there's a couple of headers which are fairly important if you're actually building, if the code that you're writing is ever going to be used on Windows. ShareLib and EPICS export are important to understand because they actually make it possible to create DLLs. So ShareLib defines a number of macros for marking library symbols to be exported and imported. So EPICS sharefunc, use that to mark a function to be exported. If you don't mark a function with EPICS sharefunc, then it will not be exported by the DLL. And actually, in later versions, you can even use these. These are used as well, or can be turned on Linux systems to determine which functions get exported by the shared libraries. So this isn't specifically limited to Windows. We're reusing the same functionality. EPICS sharefunc then marks functions. If you're wanting to mark class, then use EPICS share class. And for variables, you use EPICS share extern. If you're saying this variable is not found in this .c file, EPICS share def if this is the explicit location for the definition of the variable. So extern is for a declaration, def is for a definition. EPICS share API is a different macro, and that's the one that gets converted into standard call on Windows, which basically sets up an alternate calling convention from C. In general, I'm trying to get rid of these. There are still a number of libcom libraries that use share API, but I've been removing them. I don't think they're necessary. You can't use share API with a function that takes variable varargs or variable arguments, for instance. The API just doesn't. The standard call mechanism doesn't support varargs. What these macros get expanded out to depends on whether this macro EPICS shared symbols is defined at the time when the file sees this macro, and also varies depending upon whether the file is building a DLL or building an archive, maybe importing a value strategy from a DLL. And I'll come back to that in a moment. EPICS export it defines this EPICS export shared symbols macro, and then it includes ShareLib, and we'll see what in a moment. And there are also a few other macros in here that define lines that get needs for registration. So there are times when you need to use EPICS export, and if you do need to use EPICS export, you need to be aware what the rules are about when to use it. So if you're doing if you're using EPICS register function or EPICS export address, then you'll need to use EPICS export because it needs these macros. But unfortunately, it also sets this EPICS export shared symbols macro. What does that actually mean? If you're using to use ShareLive properly, then these are effectively the rules that you have to follow. So your header file, you need to put those keywords in your header file. So you need to include ShareLive.h and also any other libraries that are needed for the declarations in this header. So basically, your library, your header file needs to be standalone. So you need to include those other header files. And EPICS ShareLive, you need to define what those macros are. So you do that, and then you apply those to decorate the definitions in this header file as you would normally. That's for the header file, but the actual implementation of your code, the rules are somewhat more strict. So there's basically three parts to the code. First of all, you need to include all header files for code that is not in the library that you're building. So it's not in code that's in external libraries, whether that's system libraries or other application DLLs. Any external headers that are needed by the module header file. So things that you've listed up here also need to be included in here. You can't just say, well, we'll put them in there and don't worry about that, and then we don't need to do them later. That's wrong. You need to include them here as well, if they are for modules which are in a different DLL. Then we define this EPICS export shared symbols macro. And then we have to go through and include all the header files for code which is not in this source file, but is in other source files which will go into this same library, the same DLL. Because this then, by defining EPICS export shared symbols, these header files will themselves include ShareLive again, but the macros will change what they're expanded out to. So it'll include ShareLive again, but there's no protection macro that says don't include this twice. It's handled specially. So here it changes what those EPICS share macros get converted into. And so you have this basically marks the difference between external code and internal code within the same DLL. Instead of doing this EPICS export shared symbols definition, you could include EPICS export.h. In some cases, you need to for those register macros. But if you're using that, you need to make it a little bit more obvious when you're doing so. This may just look like including another header file, and somebody coming along or you coming along later on may not recognize that this is EPICS export and it has a special function. So we need to make it obvious that there's a dividing line between internal headers and external headers in there. So these are basically the rules for how to use ShareLive. There's information about that in the ShareLive.h file. So if you need to be reminded what the rules are and how to use these, go to ShareLive. If you're creating code that's never going to be built on Windows, you may think, well, I don't need to worry about that. But as I said, even now we're starting to make use of these. I have versions of these macros which are expanded even on Linux. So you might find that you say, this is never going to be built on Windows. If it's going to be built on Linux, it might matter to somebody in the future. So I would encourage you to try and understand them and put these things in, even if you think this is never going to be needed. It might be. Final slide on unit testing. LibCom also includes a header file called EPICS unit test, and this is basically a unit test reporting library which generates a standard test output protocol called the Test Anything protocol, TAP. And this has been designed to work with the build system because the build system runs test programs under a test harness that actually reads the tap input format. And for the Jenkins continuous integration system that we use here as well, that's also looks at tap output files. So test programs generally, I would suggest if you're writing test programs, it's a good idea to use this EPICS unit test stuff, and then that will make it easier to run the tests. There's also, so run tests and this tap files thing only works on workstations. For embedded systems, then we have a test harness functionality. There's some code that's actually included in the EPICS unit test stuff and in LibCom. And so we basically write harness systems that will include all your test programs and can run them one after the other. So the test library itself provides the usual sorts of operations. I'm planning to run this number of tests, an OK, which takes a pass-fail value and a string for the name of the test, or there's another macro that that stringifies the test condition. Or you can just say this is a pass and fail. In general, when you write tests, you should always try and keep the number of tests that you run the same. So there should be the same number of pass calls as there are fail calls, and the total number of pass-fail and OKs should be equal the number that you give to the plan. If you have tests that you can't run on a particular architecture or something like that, then you can use skip to say I'm skipping 3 tests because I can't run them on this architecture. And that will tell the test harness there are 3 tests skipped here. If there are tests that currently fail because you haven't actually implemented some functionality but you've already written the test for it, you can use this to-do feature where you say, I'm expecting these tests to fail, but that's okay, they're expected to fail. The harness will then say, okay, yeah, these failed, but they were expected to, so it doesn't mark them as failures really. You can also print out diagnostic messages and above? No, that was an autocorrect. That should have been abort. So you can abort test programs if the test program fails. And then when you're actually finished running all the tests, you call done, and that then triggers the harness on the embedded operating systems to say, yes, we passed 3 tests and we failed 4, those kinds of things. There's a related header file called test main, which defines a macro main, which the idea here is you want to be able to use the same test program on both workstations and embedded operating systems. But on a workstation, this needs to be a full-blown program. On the embedded operating system, it's just a function, so main basically converts, you tell it what the name of the thing is, and it either generates a main or it generates the function name for the embedded operating system. And then these work together with the build system variables, test prod, test scripts, and on 3.15 we have a test library, which, as I said, builds programs without installing them, and then the test programs then get run inside the o.architecture directory. If you have programs that you're actually wanting to run as tests, then they need to be named in the tests variable in your make file, and then when you make run tests, it will basically it will grab all the names of all those tests and run them and present the results. Or similarly, the tap files target will turn these into generated files. That is my last slide. Do we have questions on LibCom, things that I might have missed out, things that weren't terribly clear? Nope. Everybody's asleep? No. Okay. Well, thank you very much for coming then.